So the time is 2:19 p.m. and we're doing FRQ3. So part A of FRQ3 asks you to find the speed of the block just before it hits the spring. So we're given, so in part A, the given values that we're going to use is mass of the block equals 20 kilograms. And theta is 20 or 30 degrees. No, the angle of the incline is 30 degrees. And we know that K, or the spring constant, is 200 newtons per meters. And gravity is always 9.8 meters per second squared. So for part A, and also the distance that the block moves before it hits the spring is, we're going to leave that as D is 6 meters. So in part A, we're going to use the equation net force equals mass times acceleration. And we know that the net force acting on a block on an incline is force of gravity in the x direction of the incline equals mass times acceleration. And we also know that Fgx is equal to Fg, which is mg sine of theta of the incline. So when we break that down, we'll have mg sine theta is equal to ma. So we see we can cross out m and m. So we're left with a equals g sine theta, which is g is 9.8 meters per second squared. So a equals 9.8 sine theta is given as 30 degrees. So 9.8 times sine of 30 is 4.9. So A equals 4.9 meters per second squared. That is the acceleration of the block as it freely moves down the incline, the frictionless plane. So now that we have the acceleration of the block, we can use it using common form, Vf squared minus Vi squared equals 2ax. We can use the acceleration to find the velocity Vf, which would be the velocity of the block before it hits the spring. So Vf squared minus Vi is 0 because the block was at rest initially, equals 2. Acceleration we found is 4.9. And the x was given as 6 meters is the distance that it moves before it hits the block. So Vf squared, 0 is crossed out, equals 2 times 4.9 times 6 is 58.8. So Vf squared is 58.8. We square root both sides. We get Vf equals 7.668 meters per second. So that's the answer for part A. And then part B, calculate the time it takes for the mass to travel 6. So since we have everything given already, we can use the distance formula. D equals 1/2 at squared plus VIT. So we know that the distance, it wants to find the time it takes for it to travel 6 meters. So we know that D is going to be 6 equals 1/2. Acceleration is still 4.9 that we found with the block. And T is the unknown, plus the VI we know is 0 because the block started at rest. So we can cross that out. We're left with 6 equals 1/2 4.9t squared. So we multiply it out. So 6 equals 4.9 times 4.9 times 0.5 is 2.45 t squared. Divide both sides by 2.45. We find that time squared is 6 divided by 2.45 is 2.449. So we square time and we square both sides. We get t. The time that it takes for the block to travel the 6 meters is 1.565 seconds. So that's part B. Part C asks to find the distance that the spring has been compressed when the block comes to rest. So, move it up a bit. So we know that using conservation of energy, we know that the change in energy from the change in potential energy from when the block was at rest at the top of the incline, would denote that as PE top, is equal to the change in the potential energy of the spring. So as the block loses potential energy from falling down the incline, the PE spring will gain that energy. So we know that PE is mgh, and PE spring is 1/2 kx squared. So mgh, we know that h is equal to x plus 6 is the distance that the spring will be compressed, plus 6, because that's the distance. 6 is the distance above the spring that the block is initially at. So we set that equal to 1/2. K we know is 200, is given to us here. 200 newtons per meters, or newtons times meters, times x squared. So now that we have this equation here, mg parentheses x plus 6 equals 1/2 200 x squared. We'll plug in the numbers that we have. So we know mass is 20 kilograms. Gravity is 9.8 meters per second. And x plus 6 is still like that. 1/2 200 x squared. So we can distribute over here the 20 and the 9.8. We can distribute the 20 and the 9.8 to the, I forgot. So the x plus 6 is just the length of the incline, but we want the height, so it has to be sine 30. So we'll put the sine 30 in. So technically it's x plus 6 sine 30 will give you the height of the block above the ground, or above where it ends up. So we distribute sine 30, 20, and 9.8 into the x plus 6. So sine 30 times 20 times 9.8 times would be, times x would be, would be 98x, and then sine 30 times 9.8 times 20 times 6 would be 588, and 1/2 times 200 is 100 x squared. So now we're going to move it all to one side that we could have a quadratic equation. So it'll be 0 equals 100 x squared. You move 98x to the other side, so you subtract 98x. You subtract 558. We plug that into our quadratic solver, and we get x equals 2.964 meters is the distance that the spring was compressed. And then part D is the speed of the block. Part D asks if the speed of the block is a maximum at the instant that the block strikes. So when the block is going down, it asks here, is it a maximum? And the answer, no, the speed is not a maximum, because after the block hits the spring, the force spring exerted by the spring opposing the force of gravity X is not yet like great enough to balance it out. So for a bit, the block will still be accelerating downwards because of FGX. So we know that, right now it would be no, because after the block makes contact with the spring, force spring, which is the force that the spring exerts, is not yet larger than the force of gravity pulling the block down. So as long as force of gravity is greater than force spring, the block will continue accelerating in the direction that it was previously accelerating. So because this is the same direction, the speed of the block will continue to grow in magnitude. Until the force of the spring, until force spring is equal or greater than or equal to force of gravity. So that's when the acceleration will be 0. So that's when the block will stop accelerating. So that means that the maximum speed will be somewhere when the spring has already compressed, not when it has just met the spring. So in part E, it asks us to explain if the mass of the block changes from 20 kilograms to 40 kilograms, well, the answers in part A, B, and C change. So in part A, we see that the equation for acceleration here was we got mg sine theta equals ma, and during that we were able to cross out mass. So mass did not factor at all into the acceleration of the block going down. So since acceleration, for part E, since mass crosses out, acceleration stays the same as g sine theta no matter what the mass is. And since acceleration is the same no matter what the mass is, then the velocity, because in common form, the velocity vf squared minus vi squared equals 2ax, that it doesn't use anything else except for the acceleration. So since that stays the same, then we know that vf squared minus vi squared with the same a will also stay the same. So for part A, mass does not change the velocity of the block when it meets the spring. And then for part B, the question asks to find the time for the mass to travel the 6 meters. So for part B, we used the distance formula, 1/2 at squared plus vit. You see in the formula, the variables given, distance is 6 and vi is 0. It doesn't change. And the variable acceleration a, we already established that no matter what the mass is, it stays the same. So if everything stays the same, the given variable d equals 6, so we'll write it out for part B, at squared plus vit. So if d, the given, stays the same as 6 meters, and acceleration stays the same as 4.9, and vi stays the same as 0, when we plug it into the quadratics, then t will end up the same as 1.565 seconds. So both for part A and part B, the mass does not affect the answer because finding acceleration, mass cancels out. And the part A and part B depends on acceleration. But for part C, we used, here you can see that in part C, we use this equation, mgh equals 1/2 kx squared. Here the mass is an important number because it changes the answer. So if we were, instead of plugging in sine 30 to 29.8 x plus 6, we would have to plug 40 in here. So we'll do that math. Sine 30 times, now the mass is 40 kilograms, times 9.8 times x plus 6 equals 1/2 200 x squared. Do sine 30 times 40 times 40 times 9.8 times x would be 196x, and then sine 30 times 40 times 9.8 times 6 would be 1176 equals, still 1/2 times 200 is still 100 x squared. So we solve, move everything to one side. We have 100x squared minus 196x minus 1176. So using the quadratic solver, x would be 100. X would now be 4.586 meters instead of 2.964 meters. So, and then that's part E. And then part F, it asks us to find if the coefficient of kinetic friction between the incline and the block is now 0.15, we calculate part C. So in part C we had, so this is for part F. In part C we had PE, the change in PE at the top. But now because there's friction, we have to account for the work friction that's opposing. So we have to subtract work friction. Now all of that would be equal to the change in PE spring. So the thing we changed was the work friction here because there's energy loss due to the opposing work of friction. And then, so we break that down, and we'll break it down here. So we will have mgh at the top minus work friction is broken down into Fk times d equals the 1/2 kx squared of the spring. So we'll do the formula for the work friction on the side to make it easier. So work friction is equal to force of friction times the distance that the force is done. So this can further be broken down because we know that friction force is equal to the coefficient of friction times Fn, and because we're on an incline, Fn equals mg cosine theta. So we plug this into the friction force. It will be coefficient of friction mg cosine theta times distance. And once we have this, we know everything we need to plug it in. So this will plug back into here. So it'll be, now that we have everything we need, mass we know is 20 kilograms. Gravity is 9.8. H is still x plus 6 sine of 30. That's the height of the block initially. Minus, so force of friction times distance, we broke it down to mu k mg cosine theta times distance. And all that is equal to 1/2 kx squared. So we have 20 times 9.8 times x times sine of theta is the same as 98x, and then 20 times 9.8 times 6 times sine of theta is 588. That's where we're distributing everything for this term. So, and then that will be subtract mu k, we know given is 0.15. Mass is 20 kilograms. Gravity is 9.8. Cosine of 30 degrees, and the distance is x plus 6, because that is the distance that the block will have moved. X is the unknown that we're looking for, plus the 6 that we know it moves, is equal to 1/2. K is 200, and x is x squared. Okay, so now that we have everything, we can we have to distribute this one here too. So 0.15 times 20 times 9.8 times cosine times x is 25.461x, and 0.15 times 20 times 9.8 times cosine of 30 times 6 is 152.767. And all of this is subtracted, what we already have up here, 98x plus 588 is equal to 1/2 times 200 is 100, x squared. Now we're going to put it into the quadratic form. So everything moves to the other side. On one side is 0. So 100 x squared minus, this x is distributed to these numbers. So this would be, to move this to the other side, it would be adding 25.461x, and this is a positive 98x, so we have to subtract it, minus 98x, and the whole numbers, this x is also distributed here, so this is a negative 152.767, which we'll have to add to the other side, and this is a positive 588, which we'll subtract to the other side, or yes, subtract 588. And simplify the terms down. 0 equals 100 x squared. 25.461 x minus 98x would be minus 72.539x, and 152.767 minus 588 is 435 minus 435.233. And if we plug this into the quadratic solver, we'll have x equals 2.480 meters. So with the coefficient of friction on the inclined plane causing a force of friction, the new distance that the spring is compressed is 200.48 meters. The time that's finished is 2:43.